In this tutorial, I will show you how to find the equation of the tangent line to a curve at a given point. Say we have a curve given by equation y equals f of x, and we have a tangent line, which is a straight line which touches your curve at one point exactly, precisely, at one point of contact. Call it P with coordinates x1, y1. Now, there are steps to follow. The first step is to find the slope. Let's call it m, which is f prime of x1. And the next step is to actually write the equation of the tangent at the point P using the following point slope formula: y minus y1 equals m times x minus x1, where m is the slope that we found before and x1, y1 is the coordinates of the given point P. Alright, this equation can be rearranged by moving terms around and collecting like terms into slope-intercept formula y equals mx plus b, where m is the slope and b represents the y-intercept. Now, let's find the equation of the tangent line to a curve at the given point 1, 5. Now, let's implement the steps. The first step is the derivative. So dy dx is 8x plus 3. Now, the second step, we're going to take x coordinate, which is 1, and we're going to plug it in into x into your derivative. So it becomes 8 times 1 plus 3, which is 11. So your slope number, m, is 11. Now, the next step, we're going to grab this equation and plug in all these numbers, your slope and your x1 and y1, and simplify this equation. So it becomes y minus 5 equals 11 times x minus 1. So make sure we simplify this equation by distributing 11 over the brackets. So let's open up the parentheses and combine like terms. So it becomes, bring down y minus 5, 11x minus 11, and we want to bring negative 5 to the right side by adding 5 to both sides of your equation. And on the right side, we want to collect negative 11 and 5, and your final equation becomes y equals 11x minus 6. So that's going to be slope-intercept form for the equation of the tangent line to a curve. Some more problems. Okay, say we need to find the equation of the tangent to a curve f of x equals x plus 1 over x at the point x equals 2. So this is a little bit different from before, since we are not given the whole point x1, y1. We are given only x1 coordinate. But the corresponding y1 value we can find by plugging these two into the function. Let's do it a little bit later. Now, we want to first of all find the derivative of this f of x, and let's just separate the numerators in order to get the derivative. So we want to divide this slope by x, so it becomes 1 plus 1 over x, and the derivative of this is gonna be the derivative of 1 is just 0, and the derivative of 1 over x is negative 1 over x squared. So actually we want to bring this x up by changing the power into negative 1, and after applying a power rule for derivatives. And after, we also want to get back, so to bring the power down in the denominator by making this power positive. Alright, so we are done with the derivative of this function. Let's move to the next step, to the slope actually. So we're going to take this x coordinate, which is 2, and plug in into the derivative. So it becomes, so remember your derivative is negative 1 over x squared, so it becomes negative 1 over 2 squared, which simplifies to negative a quarter. That's your slope. So as mentioned before, we have to find corresponding y1 value by just plugging 2 into the original function, which is x plus 1 over x. So your corresponding y value becomes 3 over 2. So we've got the whole point, which we are going to use into this equation for the tangent line. So let's substitute all values and simplify the equation. So we've got y minus 3 over 2 equals a quarter, negative a quarter x minus 2. We're going to do the same steps. We're going to distribute and move everything around in order to get y alone on the left side of the equation. So unfortunately we have to deal with these pesky fractions, but that's okay. So your y becomes a negative a quarter x, and we have to combine these two fractions together. That's actually going to be 4 over 2, which is just 2. So that's the equation, the final equation of the tangent line to that curve in slope-intercept form.